force here is now going to go like m times that frequency squared divided by 2 times this distance of the sphere from the end mirror times the amplitude of the passing gravitational wave, and then it's going to be time dependent here on the frequency of the passing gravitational wave. And so we changed the light intensity to make this overlap. And if I have a 100-meter long cavity, you can get ring sensitivities that are at the order of 10 to the minus 22 per hertz at the high frequency end for one of these disk sensors if I have a 75 micron radius and 5 nanometer disk. And so in this case, like I mentioned before, the sensitivity in this limit is not given by the ability to measure displacement precisely, but it's limited by the thermal noise in the motion of the mechanical oscillator. And so we can kind of think about this sort of like our big giant tunable, big giant resonant bar detector, except now I have a wide tunability, right? So I have a high Q oscillator. I'm looking at this high Q oscillator to produce significant displacement when it gets acted on by the gravitational wave. But now, rather than using a piece of metal, which is pretty much living at one frequency, I can adjust the frequency and scan it by just changing the intensity of the light. So I think about this kind of as a tunable bar detector with a very wide range of tunability. So I can ask, well, what is the thermal noise limited strain sensitivity?
So,
yeah.
Again, what is the trick? Because one always hears in this business that you need really massive objects. So how did you get around that?
Well, we still actually benefit from more mass. So it turns out that for the geometry I've chosen, you could imagine taking the radius of your disk out to larger distances, but you want to basically make as much mass as possible. The limitation is that we're also using the light to levitate the object, so if it gets too heavy, it starts to fall, and also
gravity goes.
right. So if you had some way to suspend it somehow, in space or something, maybe you could, use more mass or something. But the other consideration is that this issue I mentioned last time, if we have the disk, you want it to be sufficiently rigid so that you can think of it as a single object that moves where you only have the center of mass. And if you make this thing arbitrarily large, then it starts to get floppy. The internal materials properties start to get mixing the center of mass mode with the internal modes, and then it complicates things. So yeah, so we still benefit from mass, but our mass, as you see, is significantly smaller than this. Okay, so I can what is the thermal noise limited strain sensitivity? Okay, so, well, this is due to the thermal noise limited force, right? So I have something here that goes like kT times the effective temperature of my cooled mechanical system times the gas damping rate times the background, the bandwidth, and now divided by n. So I've written this not as a minimum technical force, but as a minimum technical strain, looking at the effect of the gravitational wave here with imparts this force on the sensor. So using this as my force, I can figure out what the minimum technical strain is, H. So this term comes from the minimum technical force sensitivity, which is the same form that we're looking at. It's kT times the GAN times the damping. Now, I need to consider carefully the effects, the limitations I mentioned last time, where there's actually a correction to this formula due to the photon recoil heaving, right? So I have scattering of this object that can improve in the case of a disk geometry, but in either case, this term needs to be considered. And then I also have some heating just due to the limit from laser cooling that we've heard about so many times yesterday. So there's another effect depending on what frequency I'm working at. This actually has to be multiplied by the response function of the cavity. So I'm looking at how at what time scale the antinode in the cavity can react, right? So the cavity line width is going to play some role there. So above the cavity pole, I'm going to pay a price here. This minimum technical strain that goes like the square root of 1 plus twice the finesse of pi times sine squared of the frequency times the cavity over C. So this is just, again, the same thing. You want the cavity to respond at a frequency above the jet.
What's the bandwidth?
Oh, here, this is the measurement bandwidth, right? So suppose you had a gravitational wave source that was acting over some length of time, and I was able to signal. Right? So this B here would be the inverse of that integration time, if you like, for the magnet. This is the measurement damage. Not the.
Just one length of time it's going around as well.
Yes, that's right.
So this is also a bit counterintuitive because it looks like you don't want a cavity, right? You want.
That's right. You actually do better with the first finesse here. That's right. And so depending on what frequency you want, right? So at high frequency, you want a small. You want to push the cavity pole up to high frequency so that you can actually do measurements at high frequency. So that means there's two competing effects here. Right? Your signal is going to get stronger if the cavity gets long because there's more strain in space-time. But at the same time, if you make it too long, if your goal is to get really high frequency information, you won't get very right. So that's right. There's a trade-off there.
What's NI?
The initial phonome occupation of the sphere in the thermal bath. So this term looks like N gamma, right? That looks like KT over H bar cubed, the same thermalization rate that you can see.
Big H is just defined by the volume of the lens. You just written it like that because you want to put it on 2 lines.
Yeah, otherwise the equation is too final. Okay, so now let's look at what we can do with this system relative to other detectors. I guess I still have 5 minutes, right?
Yeah.
Okay, so so here this is the strain sensitivity in square root of hertz as a function of frequency, where now I'm starting at 10 to the 4 hertz. So this is kind of the range at which LIGO, these gravity wave detectors kind of stop their plots, right? Because their signal is continuing to decrease due to this shock noise limit, and also the known sources in this region starts to become a little bit sparse side. And so, we'll start with the red lines here. So the red lines here are what happens if you extrapolate the response of LIGO up to high frequencies. So what you see here with these dips is that at the free spectral range of the cavity, one gets a return to the condition where you could, in principle, get the same displacement measurement sensitivity that you had at DC. Right? Because now, if the mirrors are moving at some speed and that happens to correspond to the free spectral, the right frequency, the free spectral range, then everything adds together and you basically recover the original sensitivity. The reason you don't completely recover the original sensitivity is that also one needs to be careful about the wavelength of the gravitational radiation that you're detecting. And so when you have a device that's this long, now the wavelength of the gravitational wave starts to become on the same order as the device, and so one gets an additional suppression that goes like one over the frequency of the gravitational wave. If you were to extrapolate this at the high frequency, you'd see these dips that occur at multiples of the free spectral range, which is 137.5 kilohertz. And then for the advanced LIGO detector, what they're anticipating being able to do is shown in the dotted. So here, for my disk sensor, 75 microns and 500 nanometer disk, at room temperature with a 100-meter cavity, you start to become comparable to LIGO at a frequency of around 40 to 50 kilohertz. And then if you extend this down to higher frequencies at 100 kilohertz up to a few hundred kilohertz, now you're beating LIGO by more than a quarter of magnitude. And so, and also you're beating potentially advanced LIGO by close to an order of magnitude as well. And so an order of magnitude on this kind of a plot is particularly useful because what it describes, if you look at the space for astrophysical sources, is that you're essentially taking the volume area of space you're looking for and cubing it. So we're actually improving the surge volume at these frequencies by a factor of 10 to the 3, just by having a factor of 10 more sensitivity. And so as I can compare, what I have here with this disk to what I have in the case of the sphere. You can really see, there's a huge advantage here using the disk shape. So one reason for that advantage is first that I have more mass. Right? So I have more mass, I have a bigger signal. So that's why the disk line looks better than the sphere. But also, if you look carefully, you'll notice the slope of these curves is different. And that's because, so the sphere is strongly limited, in this case, by scattering of our photons in the trap, whereas the disk, because this geometry is not nearly as scattering as much, and so we gain more rapidly as the frequency increases, up until the intensity gets large enough that the scattering starts to play a role, and then this slope starts to change as it goes higher. frequencies. So there's really this, I think, illustrates that using this disk type geometry could be significantly more useful than this kind of measurement. And so I guess the final thing on this plot is the shaded region. This is from a theoretical speculation about how black holes may emit sources of high frequency gravitational waves as a result of particles that annihilate in the clouds that can form around them. I'll just say a little more about that in a second. But just to illustrate, so we're doing a comparison here with an experiment this is to scale, so a 100-meter system versus LIGO, which is 4 kilometers. Right? We're still able to make reasonably similar kinds of measurements with a machine that's a couple percent of the size of that system. So for sources, so astrophysical sources I mentioned are kind of sparse. They're sort of the natural upper bound on gravitational wave frequencies that's related to the inverse size of the smallest kind of black holes out there, and that's sort of the 30 kilohertz range. But above that, there are a couple ideas for physics beyond the standard model that could give you some kind of signal. So for example, if you have the axion, which is one of, I guess, the most well-motivated particles that hasn't yet been found, and so this particle is postulated to exist to explain why there's no CP violation of strong interactions. It's postulated as a possible candidate for dark matter. So if these things do exist, they can accumulate in clouds around black holes, and they can annihilate into gravitons and produce signals that are, some monochromatic signal that are in this range here, that are in the shaded area. There's also ideas for string cosmology, where you can get signals that are occurring at these 100 kilohertz range. And then also there's a chance of the unknown, where who knows what sort of things nature has in store for gravitational waves. High frequencies. So I think I better go ahead and conclude. And so I guess the main message that I want to leave you with is that using these optomechanical techniques, laser fluid tracking applied to these levitated dielectric objects, sort of mesoscopic AMO, which you want to give you through some rich opportunities for precision sensing, so Casimir effects, short range gravity waves, also other things that we didn't talk about, practical things, accelerometry, motion measurements, and that sort of thing. And then also could maybe lead to some interesting tests of quantum behavior at new scales, as we've heard about in some other lectures. So I just wanted to acknowledge our research team and collaborators and sponsors, and finally, just thank you